Find out what 1 degree really is.
I've been thinking about 1 degree, and I'm beginning to get a familiar feeling that I used to have studying physics, which is you start out with something that seems very simple, that you just want to define in a straightforward way, something like temperature. And the more you think about it, the deeper the layers get, and the less you feel you really understand. You know, this really isn't going to be easy for me, because I can't remember, really, in detail, anything that I studied.
Novel quantum effects in low-temperature, mesoscopic, quasi-zero-dimensional electron systems. Yep, that was the title of the PhD I embarked on here in Cambridge after completing my physics degree.
You know, this is a really fitting place to be starting this journey, because this is where modern physics started, really. This is the spiritual home of physics, the Cavendish Laboratory. This is where everything happened. Ernest Rutherford split the atom, J.J. Thomson discovered the electron, G.I. Taylor discovered the quantum nature of light. It all happened here. That's where Ben Miller studies for his PhD.
After 20 years away from the lab, I knew I'd need help. I decided to look up my old supervisor, the leading semiconductor physicist, Professor Sir Mike Pepper.
Mike was always the guy you went to put you on the right track. Mike has a brilliant way of being able to explain complex ideas really, really clearly. And just with a few words, he would just kind of put you back on the beaten track.
A couple of photographs here with you on them.
The lab photos, the Hall of Fame. There I am.
That's it.
With bleach blonde hair.
Yeah, well, there used to be speculation about which colour will Ben dye his hair next week, actually. Here's some posters, Ben, describing current work. You'll find it interesting, actually. Yeah, there you are.
Coulomb blockade, oh no, that's what I was doing.
That's what you were doing, yeah, that's right. And I think you were the first in the country to find those.
I was.
Yeah, that's right.
This is what I did. That's a quantum dot.
Yeah, that's it. You know, it's just been completely absorbed into the way of doing things now, so it's no longer discovery, it's a diagnostic tool.
Really? It's part of the technology?
Yeah, it's part of, use it for diagnostics. Yeah. Interesting, yeah.
Could have been me, Mike.
Your name should have been up there, yeah.
Could have been me.
Okay, well, this will bring back some memories for you, Ben, where you did your experiments.
It was heartening to know that my work at the lab had become part of mainstream semiconductor research, but it wasn't going to help me with my immediate problem.
So, Mike, you've been a big help in the past. When I've slightly lost my way, I thought you'd be a good person to talk to today at the beginning of my journey and my quest to get to grips with 1 degree. So I was wondering, really, if you had any pointers about what direction I should take.
That's a tough question you've got there, Ben. That's, I mean, temperature is a way of describing. We must know temperature accurately. We've got to know numbers accurately.
This is a question about measurement, isn't it, really?
Yes.
It's about how we...
Measurement is everything. Yeah, measurement is everything. I mean, if you don't feel very well and you go to your GP, the first thing that he or she will do is measure your temperature, because they've got to know. I mean, it's a measurement. You've got to know what is going on, and that's the only way you can. It's no good just waving arms and saying, I'm hot, I'm cold. You need to say, how hot, how cold? So it's a big world out there, Ben, and so you really got to dig around for your answer, actually. And I'm not sure I can help you that much, really, beyond what I've said, and I wish you good luck. And I'm intrigued to know what you come up with.
Spoken like a true supervisor.
The reality of the challenge I'd set myself was beginning to sink in. There would be no easy answers. We all know the universe contains some very, very hot things and some very, very cold things. But what do they have in common? When we measure temperature, what does it mean? With these kind of problems in physics, I always find it helps to return to basics, to get behind the thinking of the great pioneers who first worked on the idea of temperature.
30 minus 196.7 degrees. You can take it a little step back for me, just the extra caution.
Yeah.
I knew that for over 100 years, the idea of going beyond the human senses to find a scientifically reliable measurement of temperature had been one of the great quests driving forward science.
I'm going to get an ice cream headache, aren't you? Brilliant.
Over a nitrogen-cooled ice cream, Professor Hasok Chang promised to show me a basic experiment that goes to the heart of this simple but most fundamental of principles.
It feels so weird. So I've got my right hand in hot water, my left hand in cold water. What next?
Yeah, and now I want you to take both of your hands out and put them into the middle cup, which has lukewarm water, and tell me how that feels.
Okay. Oh, my word. The hand that was hot now feels cold, and the hand that was cold now feels hot.
Even though they're in the same cup of water. So this is how people realized that our bodily sensations didn't necessarily give the right measure of temperature.
And that's why you spend all your time, you know, that conversation people always have indoors. They go, is it cold in here? Is it hot in here?
Yeah.
Is it cold? Is it me? Is it you?
Yeah,
Is it me? Is it cold? Is it cold? Is the door open? Is the
If you're
heating
running
on?
a fever,
Yeah.
you're going to feel cold. And
Yeah.
so people began to think, we can't rely on the body anymore. We need an instrument, a thermometer.
So they can now measure temperature, but did they know what it was that they were measuring?
Well, this was actually a deep question, because when practical thermometry as we know it was established, which is late 18th century, early 19th century, the dominant conception of heat was that it was a fluid, which they called caloric.
A fluid?
Yes, so many people thought of temperature as the density of this caloric fluid that things possessed.
So they could measure temperature long before they actually knew what it was that they were measuring.
Yes, and it took a long time of very hard work in physics before they could say what temperature was.
Hassan, I've set myself this challenge of finding out what is 1 degree. You've written a book on this. What's the answer?
Well, Ben, it would be far too easy if I just told you the answer. Why don't you go and make yourself a thermometer? You know how the basic principles work. So go and rig one up, come back to me, and we'll go and make some measurements and see what 1 degree really is.
Hassan, I bought you an ice cream. What is it with you physicists?
When I asked Hasok to help me define 1 degree, I thought I'd get a neat and tidy answer. Instead, I now find myself returning to the very basics of temperature measurement. And surprisingly, that actually feels good.
You know, right now, I've got exactly the same feeling that I think I had when I turned up at the Cavendish Laboratory on the first day of my PhD. This is what happens in science. This is what happens in science. You know, if you want a bit of apparatus, you know, if you want to do your experiment, if you want to investigate something, it pretty much always starts with making something.
Galileo, Fahrenheit, Celsius, and now Miller. In my quest to build a simple thermometer, I was following in the steps of some of the greatest names in science.
And you'll see.
Will Floodgate of the British Society of Scientific Glassblowers had agreed to help me.
So, Will, I'm trying to get to the bottom of what is 1 degree.
Right.
And I've been set the challenge of building my own thermometer.
What do you have in mind? What's your parameters that you've got?
You know, I can't help noticing that most of the thermometers you see around are basically involve the expansion of a liquid from a sort of bulb up a very, very thin tube.
Yep.
So I thought I'd basically go for that sort of design.
I knew that if I could measure the expansion of that liquid against a defined scale, I'd have a basic measurement of temperature, and the first step towards defining 1 degree. But here's the tricky bit. To measure that accurately, first you need to create a bulb to hold the liquid, ideally without burning your lips.
Oh, it's falling off.
Turn it, turn it. Bring the into your lips and blow. And keep it turning. Blow.
So difficult.
Where's the puff gone?
Oh, I'm getting it back. I'm getting it back.
Good, good. Blow, blow, blow. Blow. And stop. You're going red.
Nothing happened. Yes, it's going. There's a tiny little bit of a bulb in. There's something in there. I'm happy with that. That's great. Wow.
The coalescing bulb.
Oh, that's fantastic. That's beautiful. That's the basics of the thermometer.
Here we go. We start to inject. And the thing is, this takes a little while.
The first thermometers used water, and it was only Fahrenheit in the early 18th century who discovered the accuracy of mercury. My choice would be somewhere between the two. Liquid alcohol.
I don't believe that is actually looking like a thermometer.
Yep, you've got a thermometer there.
Okay, so now, to define my 1 degree, I need 2 fixed points of temperature, 2 really reliable fixed points of temperature, one cold and one hot, and then I divide that difference up into 100 subdivisions, and one of those subdivisions is
1 degree.
1 degree.
Without those 2 fixed points, there'd be no way to define a scale, and no way of one thermometer ever agreeing with another.
Crushed ice. Lovely.
Oh, you beauty. Look at that. That's my cold point. So now I need to choose a hot point. Do you ever make sandwiches here?
The melting point of butter.
Just hold
Will
it
assured
up
me
there,
I'd be in
so
good company, as it had been used by some of the early pioneers of thermometry.
butter is melting.
Oh, I've got it. Hot point. There. Melting point of butter. Cold point. Melting point of ice. Nice.
I was now ready to define my scale.
Okay, well, so we've run into our first snafu here, which is the hot point on my scale is there, and the cold point is there. So there's not a whole lot of space to make my divisions into degrees. So the melting point of ice is going to be 0 millers, and the melting point of butter is going to be 5 millers. Great.
I'd done everything Hassock had asked. I'd built an accurate thermometer and defined my 1 degree using 2 fixed points. I could now measure temperature on the Miller scale.
Hassock,
Hello, Ben.
have I got a treat for you?
Oh, have you done it?
Yes, I have. So what you have here,
Oh.
this is the Miller scale,
Ah, the Miller scale.
which is currently reading, what are we at there? 1.25, I'd say, millers?
No, what are the 0 and 5 points?
Well, 0 is the melting point of ice,
Yeah.
and the 5 is the melting point of butter.
Butter.
Yeah.
That's good. That's good.
That's good.
Actually, in 1688, there was a chap called Delancey who made a thermometer with the melting point of butter as the upper point.
Oh, someone got there before me.
Yeah, well, but I think you got a problem because, first of all, no one else is going to know what the Miller scale means if you gave numbers on that. And if they were to try to make the same thermometer as you did, they're going to have exactly the same butter as you used because different butter will melt at different temperatures. Top marks for effort, but I'm afraid you're not quite there yet.
Well, I don't feel my time's been completely wasted because, you know, building this has given me a really good understanding of the basic principles. But what I still haven't got is that scientific accuracy. Oh well. The Miller scale is dead.
Yeah.
I was realizing a great truth about 1 degree, that ultimately you can define it in any way you like. But for it to be scientifically meaningful, everyone has to agree to the same system. A system I need to understand if I'm going to get to the bottom of what 1 degree really is. There was only one place left to turn to, the National Physical Laboratory in South London, where that 300-year-old quest for scientific accuracy has been elevated into a religion. If one of my fixed points is wildly inaccurate, I want to know what the professionals use. Graham Machin and Michael de Podesta promised to show me.
Well, we have some in here, in this container, some triple points.
Yeah.
So-called triple points of water.
So when you say triple point, I can see there's like crushed ice in
Yeah,
here.
okay. So a triple point is where a solid, a liquid, and the vapour of the same substance are in equilibrium with each other.
Graham explained to me that, strange though it may sound, at the triple point, water is present as liquid, ice, and vapour. And that's only possible at one unique temperature.
So inside here now is only water. There's water vapour,
Yeah.
there's liquid water, as you can see, and there's ice.
Right,
And
yeah.
that's a unique temperature.
Just
Essentially, it's really just
at
yeah.
this point here is the triple point of water.
right.
The holy grail for thermometrists.
Benchmarking your thermometer to this unique fixed point gives you extraordinary precision. And from that, in turn, comes extraordinary accuracy.
How accurate are they? What would be the discrepancy? How close do they agree?
Well, they're amazingly accurate. Recently, we compared some triple point of water cells from MPL with our colleagues across Europe, and they agreed to within 20 millionths of a degree.
20 millionths?
20 millionths of a degree.
Wow.
Yeah. And we do have to go. Yes, of course you can. There's one in this box here, which I'll hold very carefully. But the very neat thing is that wherever you are in the world, they all follow the same temperature scale. So whether you have this thermometer calibrated here in the UK or in the US or in Australia, they will all realise, or China, they will all realise the same temperature to within a few millikelvin or even slightly smaller than that.
So much of what we take for granted in temperature, being able to reliably know that the medical thermometer that we measure our child's fever with, or the food that we buy in the supermarket, is kept at a controlled, known, reliable temperature. That's really fundamental to the way that our society operates. And, you know, without this place, life in contemporary Britain would be as meaningless as if everything was measured on the Miller scale. You know, I don't really feel that I've completely got to grips with what a degree is, but I feel absolutely sure that we can measure it.
I finally feel I'm making progress, that I'm getting back some of my old physicist's know-how. And at last I feel ready to take my place alongside the scientific community, to start making my own measurements of temperature. To build a more accurate map of Britain's variable weather, I knew the Met Office were launching an initiative to encourage members of the public to submit their own weather readings.
Met Office stream.
They could count on my support.
Whoa! Look at that. Okay. Oh, this is the gold here. The instrument under test was calibrated by direct comparison against an SPRT thermometer having calibration traceable to national standards, immersed in a closely controlled reference temperature environment. Readings were taken with a viewing magnifier, and the thermometer stem was lightly tapped prior to each reading. The following results are derived from the mean average of a number of repeat readings. Accurate to within 0.02 degrees centigrade, 2/100ths of a degree. It's pretty accurate. If I were to insert that rectally, I would know your body temperature to within 0.02 degrees centigrade. That's good enough for me. There we go. So, what we want is maximum.
I know I've got to put in the hours, but I'm genuinely excited that data from this weather station on my roof in the centre of London is going to be playing a small part in the British system of temperature measurement.
Wow, 27.2.
But there's something I still don't feel I've quite got to the bottom of. Yes, I might be able to measure 1 degree to an incredible level of accuracy. But measurement is one thing. I still don't feel I can really describe what 1 degree actually represents. It took the work of a Victorian gentleman to open the door on the amazing world of what temperature fundamentally is. James Joule wasn't a professional scientist at all. He was a brewer.
Okay, so this is where the vats are. Fantastic.
Brewing requires a very careful control of temperature, and it turned Joule into a real master of accurate temperature measurement.
Whoa! It's a beer fountain. Just a sec. Yeah, it's coming on.
True to the spirit of the age, Joule devised an experiment. Inspired by his brewer's know-how, Joule's simple experiment uses a falling weight to churn up a container of water. He believed it would establish something fundamental about what heat really is.
The sort of rising excitement you get when you're doing an experiment. You're suddenly about to, you know, done all these little fiddly bits, and then suddenly you're about to get an answer.
According to Joule's theory, the experiment should cause the temperature of the water to rise. If he was right, it would revolutionize our understanding of temperature.
The initial reading is 27.4, yeah.
Desperately imprecise, of course, by Joule's standards. He claimed to be able to read to within 1/200th part of a degree, and that's Fahrenheit.
I think if you feel ready, time for a boost. I feel ready. Do you feel ready for a boost?
I feel ready.
Okay. Come on, you beauty. Okay. 27.6, 27.7. Any increase on 27.7? Might even go 27.75. It's halfway between those two marks. 27.75. Come on!
Just over 0.3 of a degree. But for Joule, that proves something fundamental.
So, the motion of the paddles has pushed the molecules of the water around, made them go faster. We're reading that as an increase in temperature. We're reading that as an increase in heat. In other words, heat itself is a type of motion.
Heat is a mode of motion. That's what we think now. That's what Joule thought then at a time when a lot of people didn't. He uses the term vis viva. Latin means kind of vital force. There wasn't even an English word for this mysterious property that people like Joule said was conserved. But the name that we give to it now is energy. And
the unit
the unit
now?
of energy in the SI system is the joule.
Energy. Here at last is the fundamental entity I've been looking for. The thing that explains what temperature really is. And according to Professor Jim Al-Khalili, apparently these dodgems are the perfect place to get to grips with it.
Dodgems?
That's why I brought you here. You'd think it'd be quite random. I mean, it's fun.
Yeah.
But actually, there's a very serious analogy, a connection. The way the dodgems bump into each other, move around randomly, is pretty much what goes on down at the molecular level. It's molecules behaving like dodgems, bashing into each other, and it's that movement, that energy that the molecules have, that defines what temperature is.
So heat is a form of energy?
Well, this is the profound thing. Actually, there's no such thing as heat.
What?
You can do away with heat entirely. There's no such thing as heat. When something's temperature goes up, something else is going on. It's not about heat. It's not about some sort of mystical fluid being transferred around. It's something going on down at the molecular level. And that's what temperature is all really about.
So when its molecules are moving slowly, a thing is at a lower temperature. And when they speed up, the temperature's higher. And that, at its most basic, is what temperature is.
So when I look at the thermometer on my roof, basically, I mean, that thermometer is burrowing right down into the motion of the air molecules around it.
Yeah. What it's measuring is how energetic these air molecules are bashing into the thermometer glass.
Yeah.
They're transferring that energy, that momentum, to the glass and then to the mercury. And then the mercury atoms are getting excited and vibrating, and that makes the mercury expand, and so you get a higher reading.
So now we know. There's no such thing as heat. Instead, what matters is energy.
It is a fundamental concept, probably the most fundamental concept in physics. But there are different kinds of energy. For me, energy is the ability to do something, to do work. So, if you have energy, you can do stuff. If you don't have any energy, you don't do stuff. And that sort of applies all the way down to the level of molecules.
I love the way that this subject of temperature and heat, the further we dig down into it, the bigger the mysteries and the more fundamental.
That's right. I mean, you think you understand it, and then you realise there's another hidden layer underneath that sort of explains it, but in another way makes it. Well, for me, it makes it richer. I mean, some people might think, oh, no, that just makes it complicated. I'd much rather prefer the simple transfer of heat.
Yeah.
But you're getting down to the nitty-gritty, the real sort of nuts and bolts of what it actually means.
I wonder how that distribution of molecular energies is looking in my thermometer this morning.
Very light cloud, beautiful sunshine. Present temperature is 16.2. Maximum is 20.5.
discovery that temperature is simply an expression of the energies of molecules led to a startling conclusion. If you cooled something down so much that you completely removed its energy, then that would be the coldest you could go. They call this temperature absolute zero, and it's always fascinated me, because as things get colder, they also get stranger.
This low temperature physics is kind of my home turf, you know. It's where all sorts of weird and wonderful stuff happens, and it's going to be emotional.
I want to rediscover the amazing things that happen when stuff gets so cold its molecules have virtually no energy. I'd come to one of the world's leading low-temperature laboratories, the Clarendon in Oxford, where they promised they could show me.
Good afternoon, gentlemen. I bought you some flowers. Cold things are different to room temperature things. It's like a different world, isn't it?
It's a different world, yes.
So everything is in a much lower energy state. Very brittle. Yeah.
Professor Robert Taylor wanted to show me an experiment that opens a door on what happens at some of the coldest extremes of temperature physically possible.
So that's the nitrogen going in.
Yeah, we're going to pre-cool the outside of the...
There's two jackets. There's an outside jacket and an inside one.
That's right. As you cool things down, they slow down. Eventually, of course, they'll just stop. And when they stop, that's zero.
No motion, no temperature.
Motion, no temperature.
Has anyone ever got to zero?
No, you can't do it.
Why not?
You can never get there.
Why is that?
Because every time you try and cool it down a little bit more, you have to start again and cool it down a bit more, and then you cool it down a bit more, and you cool it down a bit more, and you gradually get closer and closer and closer, but you never quite make it.
What's the closest anyone's ever got?
Depends in which system you're talking about. In nuclear spins, they got down to a nanokelvin, which is 10 to the minus 9. That's 9 zeros after the decimal point.
That's 1,000 millionth.
1,000 millionth of
a degree.
Degree, yes.
Above zero. I'm just opening it ever so slightly, like this.
Yeah.
Oh, wow, we're getting close to 3 Kelvin.
Keep going, keep going, keep going.
Still?
Even if this absolute zero can't be reached, Robert promised he could take me close, liquefying helium to temperatures where our ordinary sense of reality is completely reversed.
And as the pressure drops above the helium, its temperature is dropping. And so eventually this will drop down to about 2.17 degrees above absolute zero. And something magical happens there when it turns from this normal kind of helium into a helium called superfluid.
What happens then? It goes sort of still.
Yes, completely still. Yeah.
Oh, wow.
There
It's gone
it is.
completely
It's gone completely still.
It's gone
It's gone
completely
through this
still.
position now. That is now sitting there at 2.17 degrees above absolute zero.
Wow, it's gone completely still.
Yeah, that's because the
No
entire
bubbles at all.
liquid is sitting there at the same temperature.
Look at that. And what is it? You know, what am I looking at? It doesn't look like a liquid almost.
No, well, what's happening here is that every single atom in that helium liquid is sitting there behaving in what's called a cooperative state. They're all behaving together.
Yeah.
So that nowhere is a different temperature. Everything's the same temperature everywhere inside that liquid.
As the helium atoms turn into a superfluid at that critical temperature, their fundamental quantum nature asserts itself. Instead of individual atoms bouncing around, the atoms move together as if they were of one mind.
Okay, Ben, what I have to do now is to lift the bucket out of there and see what happens.
Which one's the bucket? That one?
This one here.
Okay.
Where normally the solid glass bucket contains the liquid helium, once a superfluid, that very idea that things are solid and can be contained no longer holds.
Now watch the bottom of the bucket. You see the drips coming out and landing on the surface of the liquid?
Yeah.
That's the superfluid helium coming out from the bottom of that plug. That plug was actually perfectly happy to hold the ordinary helium, but because this is superfluid, it actually pours out of the bottom. And you can see the drips is coming off and landing onto the surface. You can see it just pouring out.
Now this is really strange. As a superfluid, the liquid helium has no viscosity, so instead of being held by that solid plug, it now runs straight through it.
It's a real quantum effect.
It's like a window on the world of quantum mechanics.
It is.
What an amazing thought that really, this is what matter is really like. All this stuff that we're made of, this is what it's really like. And its real nature just gets obscured at room temperature because of all the vibration and all the thermal energy. This is really what we're made of. We're made of weird stuff like this. That is mind-blowing, isn't it?
It's also very cold. That's at 2.17 Kelvin, or 2.17 degrees above absolute zero, and that actually is colder than outer space.
You know, when I started this journey, I was expecting to get to grips with something,
to approach through accuracy and measurement a real, knowable, fundamental reality. And actually, I've gone through the rabbit hole and I've ended up somewhere I just never expected to be, and it's disturbing because what I've discovered is that as temperature decreases, as we get closer and closer to absolute zero, we pass into a completely new world, the quantum world. And it's baffling and it's weird, and temperature, you know, the random thermal motion of molecules. In a way, you can think of it as being the thing that obscures that weirdness and makes our lives livable. Beautiful day. Present temperature 15.8, maximum 17.7, minimum 11. I think it's going to be a lot hotter than that today. It is just switched on. I'm actually resetting my maximum thermometer, just in case you wondered. As I come up here every day to make my measurements, I'm starting to see beyond those simple numbers on my thermometer. And I'm beginning to get a sense of this deeper, underlying entity, energy, that ebbs and flows through everything according to the fundamental laws of physics. Very mild day, a bit windy. And for the first time in 20 years, it's made me reflect again on the vast role energy plays in our universe, about where it comes from and where it's going to. Professor Peter Atkins of Oxford University had invited me to join him in watching some films, with the promise he could help answer my questions. I can't help noticing, when I look around me, it's always hot things that cool down. You rarely see cool things heating up of their own accord.
Yeah.
And there's something really fundamental going on there, isn't there?
That is the most amazing insight into the nature of things going on in the world, that things cool down because the energy that was originally in this cup of coffee is spreading into the surroundings. So, and the insight that you're talking about is that effectively things are getting worse.
So, if you're saying that hot things always cool down, your cup of coffee always cools down.
Buildings fall down.
Buildings fall down, my desk gets messier and messier at home.
Everything disperses.
Disorder drives the universe.
Collapse into disorder is the spring of the universe.
Wow.
And I think it's fantastic to know that this natural process of energy spreading in disorder, of matter, atoms, molecules spreading in disorder, is actually what drives every process that happens in the world.
So the whole universe is descending into disorder, and that's what we can see on the screen. You know, we don't see rubble suddenly righting itself, coming up into form a building. All these processes, we see that the amount of disorder is always increasing. That's a very depressing thought, Peter.
Absolutely. And you should be depressed. Because things, you know, the spring of change is that the world is getting worse. But it's getting worse in an extraordinarily interesting way. All processes on Earth, the opening of a flower,
yes,
all the processes of the evolution of the biosphere, for example, are really just elaborate manifestations of this dispersal of energy.
Where's this going to end? I mean,
well, you can guess where it's going to end, when there's nowhere left for more dispersal to take place.
Everything will be at the same temperature.
Everything at the same temperature, yeah. There will be the heat death of the universe.
So everything is getting colder and colder and colder. Bummer. Still, let's not get too depressed. The sun's still got enough fuel to last us another 4 billion years. If only we could replicate some of that awesome power, we'd solve our own energy problems at a stroke. amazement, there's a place where they're actually trying to do just that. Tucked away in the Oxfordshire countryside, the Joint European Torus is a project to try and create nuclear fusion, the process that drives the sun. To succeed, they need to reach temperatures at truly intimidating levels.
Wow. Joe, so how hot does it get here?
It gets to about 100 million degrees centigrade.
100 million degrees centigrade. What's the temperature of the sun?
About 15 million degrees centigrade.
So, of the order of 10 times the temperature of the sun. That must be one of the hottest things in this galaxy. Why does it need to be that hot?
Well, we want to recreate the process that fuels the sun, and that's the fusion of hydrogen into helium.
Yeah.
And because hydrogen nuclei have the same electric charge, they repel each other. And to get them to fuse, to join together, we need to collide them at really high speeds. And that's fundamentally what temperature is.
Yes.
It's a measure of the speed that particles are moving at.
Temperature is a measure of the speed that molecules are moving at. Yes, that's I'm really getting to grips with that now.
It's amazing to think that our control of temperature has gone so far that we can actually think about replicating the process that fuels the stars. To get the hydrogen to such high speeds, they've built a vast donut-shaped magnet just 3 meters across. So far, they've only managed to sustain the fusion reaction for just a few seconds. But for me, the possibility of using science and technology to create a clean source of energy is one of the most exciting ideas around.
Wow. It's like setting this in a science fiction film.
It's rather, isn't it?
I love it. Now, I'm a bit of a temperature measuring professional myself. I don't want to make a big deal about it, but I've actually made my own thermometer. However, I'm pretty sure my thermometer wouldn't cope with a temperature 10 times the temperature at the centre of the sun. How do you measure the temperature accurately? How can you get an accurate measure of a temperature that hot?
We actually have one physical device that darts into the plasma to measure right at the edge where it's coolest.
Yeah.
It would actually be probably a few million degrees, but it darts in very quickly.
Brilliant.
Just
and what about the middle? What about the middle where it's like...
In the middle where it's 100 million. We have to use laser-based techniques to measure the temperature. We shine a laser in and look at the light that comes back.
And that gives you a really accurate figure without actually having to touch the...
Yes,
plasma.
a non-invasive technique.
Wow. Respect.
I think at last I've got a sense of what lies behind that simple measurement of 1 degree on my thermometer. Going back to the woman at the dinner party who got me started on all this, I certainly feel I could have a decent stab at explaining it to her. But her questions weren't simply about that scientific idea. They were about what a temperature rise of 1 degree means on average. And that's where things get a bit messy. I was back in Cambridge to meet someone I hoped could help me.
So I was having this conversation, and it became apparent that she didn't really know what an average was. So that, when you might say the average had increased by a degree, to her that didn't really sound very much because, every day the temperature varies by much, much more than that. And I slowly realised I didn't really know what an average was either, sufficient to be able to explain it. And I thought you'd be the right man to talk to.
Okay, well let's move away from temperature and think about another thing we can measure, like people's height. So we talk about this is a scale of people's heights, and if we draw a curve like this, where this shows sort of how many people there are of each height. So this is sort of people of average height, there's lots of them around, and then you've got short people down here, and there's a few of them, and you've got really tall people here, so 6'6", something like that, and you've got a few of those. So let's mark in a really tall person. So at the moment, you've got that many really tall people.
Yeah.
So that might be, 1 in 1,000, 1 in 10,000, something like that.
6'6".
Yeah, something like that. So let's say, though, that everyone grew an inch. Everyone got an inch taller. Now, what would happen then is that this distribution would shift a little bit to the right.
Yeah.
Now, right about the middle, you wouldn't notice very much at all. You wouldn't, if everyone in the street was an inch taller, I don't think you'd notice the difference. But if you're only looking at really tall people, Now, you've got a much bigger area.
Bigger area.
The proportion of people who are really tall has really gone up a lot. Now, if we put that into temperature, what that means is that days that are really stinking hot in the past, and they happen very rarely, you only have to move the mean temperature up a bit, the average temperature up a bit, and the number of those days will really go up a lot.
In other words, if we're talking about temperature, say a rise of only a degree or so in average temperature will produce many more very, very hot days.
Yeah, if we define a hot day as something that's really uncomfortable, it's not dangerous, so very rare at the moment, those will become a lot less rare.
As I've gone deeper into the underlying science of temperature, one thing that's really stayed with me is the value of measurement. Whether it's 1,000,000 degrees...
wow, we're getting close to 3 Kelvin.
A fraction above absolute zero.
That is mind-blowing, isn't it?
Or taking readings on my rooftop. I've realised that measuring temperature isn't simply a question of fundamental physics. It matters to all of us. The Earth's average temperature has already increased by 0.75 of a degree in the past 150 years, and it's set to rise even further. That's why, for me, perhaps some of the most interesting measurements are taking place right here, in London W1.
Lift going up, doors closing. The lift is now travelling at 1,400 feet a minute.
Nice one.
Dr. Janet Barlow is one of a new breed of meteorologists.
Fantastic, isn't it?
She's managed to place a weather station somewhere that's been closed to the public for almost 30 years. On the top of the BT Tower, 191 metres above London.
And we've got the city over to your right.
Everything? Oh, yeah, of course. Brilliant. You know, I'm really surprised to know that finding out what's going on in terms of temperature in cities is a new area. You know.
Well, I think we've had a lot of heatwave events recently, and with concerns for the future, we may get more heat waves. But in cities, they're particularly intense, and we know from 2003 many thousands of people died in cities across Europe because it was so hot. So this is a real concern for the future, especially as cities like London are going to expand. So those urban temperature effects are only going to get worse.
I heard you had to kind of sneak up here to start with.
You think about things in a very abstract way, and we have been thinking for so long, wouldn't it be nice to get a temperature measurement, a wind speed measurement above London?
Yeah.
And we just happened to be walking out of a meeting, and there was the BT Tower right in front of us. So I thought, well, you don't get it if you don't ask.
Yeah.
So I came and talked to the security guards, and
Yeah.
beyond that, we came and made some measurements within a few weeks.
I really admire scientists like Janet. She's investigating something that ought to concern everyone. Because as cities like London continue to grow, they're going to keep getting hotter and hotter. And that's without even thinking about what climate change will do to temperatures.
So, Janet, this is like a new frontier in temperature measurement, isn't it? You're right, you know, you're right at the vanguard. You're doing something no one's done before.
Yeah, I mean, the BT Tower is a really unique building in London. It's so exposed to the atmosphere compared to any other structure that we have a really clear idea of what's going on. And from the initial results that we've seen, having a temperature measurement up here compared to what we've got on the ground is giving us huge insight into the way that heat is being carried from the urban surface up to the air above, particularly at night time when those hot temperatures are occurring.
So, going to show me your weather station then?
Oh, yes, of course.
How are you with heights, Janet?
Oh, I'm fine there. No problem.
Yeah, me too. I'm great. Really good. Well,